Hello there, and welcome to this quiet space where time moves slowly and the Earth itself becomes our guide. Tonight, we're traveling backward, not through centuries or even millennia, but through hundreds of millions of years, to a world that would feel both familiar and utterly strange. We're going to a time when the air was thick with carbon dioxide, when the oceans were warm and shallow, and when life on land was still learning what it meant to grow tall, to put down roots, to reshape the ground beneath it. This is the story of the Late Devonian, a period that stretched from 419 million years ago to 359 million years ago. It's a story about what happens when the atmosphere changes, not over decades or centuries, but over millions of years. When carbon dioxide levels that had kept the planet warm for over 100 million years began to fall, dropping by roughly half, the Earth responded in ways that would reshape its climate, its oceans, and the very life that inhabited them. Before we begin, I'd like to know where you're listening from tonight and what time it is where you are. It's a strange thing, isn't it? To be separated by distance and yet connected by curiosity about a world that existed when no human eyes could see it, when the continents themselves were arranged differently, when even the stars overhead followed different patterns. No matter where or when you are, I'm glad you're here. If this kind of slow unfolding of deep time speaks to you, I'd be grateful if you tapped like or subscribed. It helps others find their way to these quiet explorations. But there's no pressure, only an invitation to settle in, to let your thoughts slow to the pace of geological time, and to let this story carry you gently through the long transformation of an ancient world. The Earth of the early Paleozoic was a planet locked in warmth. For over 100 million years, atmospheric carbon dioxide had maintained concentrations far beyond anything measured in human history. These levels ranged from 4 to 20 times the amount present before the Industrial Revolution, which scientists commonly reference as approximately 270 parts per million. In the mid-Devonian, the atmosphere likely held more than 1,000 parts per million of carbon dioxide. In earlier Paleozoic times, concentrations may have exceeded 2,500 parts per million. These numbers represent more than abstract measurements. They describe a fundamental planetary condition, a thick thermal blanket wrapped around the Earth, trapping heat that would otherwise escape to space. This is what scientists call radiative forcing, the way certain gases absorb and re-emit infrared radiation, keeping the surface warmer than it would otherwise be. The greenhouse effect was not weak or temporary. It was persistent, powerful, and stable across geological epochs. The sun during this period was dimmer than it is today. Stars like our sun gradually brighten over billions of years as they age. 400 million years ago, the sun's output was measurably lower, perhaps 3 to 4% less intense than present levels. Without the elevated carbon dioxide, the Earth would have been significantly colder, possibly locked in ice. Instead, the greenhouse gases compensated for the weaker sun, maintaining global temperatures well above modern averages. This was not a world of ice caps or seasonal extremes in the way we understand them now. The poles were temperate, perhaps cool, but not frozen. There were no vast Antarctic ice sheets, no Greenland glaciers kilometers thick. The oceans extended far onto the continents, creating broad, shallow seas where warm water bathed the edges of the land masses. These epicontinental seas were not deep trenches but wide platforms, sunlit to their floors, rich in dissolved minerals, ideal for certain forms of life. The land itself was still relatively barren in the early part of this story. Vascular plants, those with internal transport systems for water and nutrients, had only recently begun to colonize the terrestrial environment. The earliest forests were not yet the towering ecosystems they would become. Instead, low-growing vegetation clung to moist areas near rivers and coastlines, slowly adapting to the challenges of life outside the water. The interior of continents remained largely empty, exposed rock and soil with little to stabilize it, little to hold moisture, little to begin the chemical transformations that would later change everything. The carbon dioxide in the atmosphere was part of a cycle, though the mechanisms regulating it were different from today. Volcanic activity released carbon dioxide from the Earth's interior, adding it to the atmosphere over time. Weathering of rocks removed carbon dioxide, though this process was relatively slow without the biological acceleration that would come later. The balance between these inputs and outputs determined atmospheric concentration, and for a long time, that balance favoured a high carbon world. In the oceans, the warm water held less dissolved oxygen than cooler water would. This is a simple physical property, the solubility of gases decreasing as temperature rises. Yet life had adapted to these conditions over millions of years. The creatures inhabiting the Devonian seas were not struggling for oxygen in the way that modern marine life would in such warm water. They had evolved in these circumstances, their metabolisms tuned to the available resources, their body plans suited to the chemical and physical environment. The climate was not uniform across the planet. There were still variations in temperature and rainfall, still seasonal patterns, still regional differences. But the overall state was warm, the poles were accessible, the tropics were not lethally hot, and the distribution of heat across latitudes was more even than it would be in later, colder periods. This warmth persisted not because of any single year or decade of unusual conditions, but because the atmospheric composition remained stable over timescales measured in millions of years. This stability was about to end. The Late Devonian would see a transformation as profound as any in Earth's history, driven not by asteroid impacts or massive volcanic eruptions, though these events would play roles in later extinctions, but by something quieter, slower, and ultimately more powerful. The change would come from the land, from organisms that were just beginning to master the challenges of terrestrial life, from roots pushing into rock, from chemistry accelerating in ways the planet had never experienced before. Understanding the composition of an atmosphere that existed hundreds of millions of years ago requires indirect methods. There are no preserved samples of Devonian air trapped in ice cores, no ancient barometers recording daily measurements. Instead, scientists rely on proxies, chemical and physical traces left in rocks and fossils that respond predictably to atmospheric conditions. One method involves examining fossil soils known as paleosols. When carbon dioxide dissolves in rainwater, it forms a weak acid called carbonic acid. This acid reacts with minerals in soil, leaving chemical signatures that depend on the concentration of carbon dioxide in the atmosphere at the time the soil formed. By analysing the mineralogy and geochemistry of ancient paleosols, researchers can estimate past carbon dioxide levels, though these estimates carry significant uncertainty. Another approach uses the stomata of fossil plants. Stomata are tiny pores on leaf surfaces that allow gas exchange, carbon dioxide in and oxygen out. Plants adjust the density of stomata in response to atmospheric carbon dioxide levels. When carbon dioxide is abundant, plants can get away with fewer stomata because each pore captures more of the gas. When carbon dioxide is scarce, plants increase stomatal density to maximize uptake. By counting stomata on fossil leaves and comparing them to modern relatives grown in controlled conditions, scientists can infer ancient atmospheric concentrations. Carbon isotope ratios, preserved in marine carbonates, provide another line of evidence. The ratio of carbon-13 to carbon-12 in these rocks reflects the global carbon cycle's state at the time of deposition. While this method does not directly measure atmospheric carbon dioxide, it helps constrain the size of various carbon reservoirs and the rates of transfer between them, which in turn allows modelling of atmospheric levels. Geochemical models also contribute to these reconstructions. These models simulate the carbon cycle over geological time, accounting for volcanic outgassing, weathering rates, organic carbon burial, and other processes. By adjusting parameters to match known constraints from the rock record, including sediment types, fossil distributions, and isotopic signatures, these models produce estimates of past atmospheric composition. The convergence of multiple independent methods strengthens confidence in the general picture, even when precise numbers remain elusive. For the early to middle Devonian, these approaches consistently point to carbon dioxide concentrations well above 1,000 parts per million. with some estimates reaching several thousand. The exact value at any given moment is less important than the overall magnitude. The atmosphere held several times more carbon dioxide than pre-industrial levels, enough to maintain a strong greenhouse effect. The decline in carbon dioxide during the Late Devonian is recorded in the same proxies. Paleozoic chemistry. Shifts, indicating exposure to water with lower carbonic acid concentrations. Stomatal densities on younger plant fossils increase, consistent with plants adapting to lower atmospheric carbon dioxide. Carbon isotope excursions in marine carbonates reflect massive changes in the global carbon cycle, including the burial of organic carbon that would otherwise have returned to the atmosphere as carbon dioxide through decomposition. The magnitude of the decline, approximately 50% from peak levels, represents a profound shift in planetary energy balance, reducing carbon dioxide from, say, 2,500 parts per million to 1,250 parts per million significantly weakens the greenhouse effect. While the relationship between carbon dioxide concentration and temperature is not linear, the change is sufficient to alter global climate state, moving from a stable greenhouse into a period of instability and cooling. This decline was not instantaneous on human timescales. It unfolded over millions of years, a rate that would seem impossibly slow in day-to-day experience, but qualifies as rapid in geological terms. For organisms adapted to stable, warm conditions over tens of millions of years, even a slow change can become catastrophic if it persists long enough, if it pushes temperatures beyond tolerable ranges, if it alters the chemistry of the oceans, if it drains habitats through sea level changes. The mechanisms behind this decline were not immediately obvious from the rock record alone. Early researchers noted the climate shift, the appearance of glacial deposits, the changes in marine life, but connecting these observations to a specific cause required understanding how the Earth's carbon cycle could be accelerated. The answer lay not in the atmosphere or oceans directly, but in the interface between rock and life, in the soil, in the rhizosphere, in the chemical zone where roots meet mineral grains. The title of this documentary refers to a 50% decline in atmospheric carbon dioxide, a phrase that might sound abstract until placed in context. In modern discussions of climate change, a 50% increase in carbon dioxide from pre-industrial levels has driven measurable warming, altered weather patterns, and raised concerns about future impacts. The Late Devonian experienced a change of comparable magnitude, but in the opposite direction, a halving of concentrations from their peak. This decline did not leave the climate unchanged. Carbon dioxide is a greenhouse gas, which means it absorbs and re-emits infrared radiation, trapping heat that would otherwise escape to space. The strength of this effect depends on concentration. Doubling carbon dioxide does not double warming. The relationship is logarithmic, but the effect is still significant. Halving carbon dioxide from very high levels reduces the greenhouse effect enough to initiate fundamental changes in climate state. The Earth's climate system has feedback mechanisms that amplify or dampen changes. One of the most important is the ice albedo feedback. When temperatures drop enough for ice sheets to form, the white ice reflects more sunlight back to space than darker rock or vegetation would, cooling the planet further. This feedback can turn a moderate cooling trend into a full glaciation. In the Late Devonian, the carbon dioxide decline pushed temperatures low enough to trigger this feedback in the southern hemisphere. Another feedback involves the carbon cycle itself. As weathering accelerates and carbon dioxide is removed from the atmosphere, the cooling reduces weathering rates, which depend partly on temperature. This negative feedback should theoretically stabilize the system, preventing runaway cooling. However, in the Late Devonian, biological factors overrode this stabilizing mechanism. The expansion of plants with deep root systems meant weathering remained elevated even as temperatures fell, driving carbon dioxide lower than the physical system alone would have allowed. The rate of change matters as much as the magnitude. Ecosystems can adapt to gradual shifts over millions of years through evolution, migration, and ecological reorganization. But even geological rates of change can outpace adaptation if conditions swing too far or oscillate too rapidly. the Late Devonian climate did not shift smoothly from warm to cool and stabilize. Instead, it entered a period of instability, with repeated swings between cooler glacial episodes and warmer interglacial periods, driven by the growth and retreat of ice sheets. These oscillations are recorded in sedimentary rocks as repeated cycles of sea level change. When ice sheets grow, water is locked on land and sea levels fall globally. When ice melts, water returns to the oceans and sea levels rise. The rock record shows multiple such cycles in the Late Devonian, each representing a swing in climate state, each stressing. Marine ecosystems adapted to stability. Organisms that could tolerate gradual cooling might not survive repeated rapid fluctuations. The comparison to the modern 50% increase in carbon dioxide is not perfect but instructive. Both represent major perturbations to the carbon cycle, both driven by biological activity, though in opposite directions. In the Late Devonian, plants removed carbon dioxide by accelerating weathering and sequestering organic carbon. In the modern era, humans release carbon dioxide by burning fossil fuels, those same organic carbon deposits laid down partly during the subsequent Carboniferous period. The timescales differ, the modern change occurring over centuries rather than millions of years, but both demonstrate the sensitivity of climate to atmospheric composition. Understanding the 50% decline also requires appreciating the baseline from which it started. A 50% reduction from modern pre-industrial levels of 270 parts per million would yield 135 parts per million, dangerously low for plant photosynthesis and insufficient to prevent severe glaciation. But a 50% reduction from 2,500 parts per million still leaves 1,250 parts per million, well above modern levels. The key is the crossing of thresholds, the points at which climate feedbacks activate and system behavior changes qualitatively. The Late Devonian carbon dioxide decline reset the Earth's thermostat. For over 100 million years, the planet had operated in a greenhouse mode, warm and stable. The decline broke that stability, initiating a transition toward the icehouse conditions that would characterize much of the subsequent Carboniferous and Permian periods. This was not a brief anomaly, but a permanent shift in the Earth system's operating state, driven by the irreversible expansion of terrestrial ecosystems capable of accelerating the carbon cycle. The warm Devonian seas supported ecosystems unlike any found in modern oceans. The most distinctive features were the reef systems, vast structures built not primarily by corals as today, but by organisms called stromatoporoids. These were sponge-like creatures, though their exact biological classification has been debated. They secreted calcium carbonate skeletons, layer upon layer, building massive domed or branching structures that could dominate shallow marine environments. Stromatoporoids thrived in warm, sunlit waters where calcium carbonate could precipitate easily. The high carbon dioxide atmosphere of the early Devonian, while driving global warmth, also affected ocean chemistry. When carbon dioxide dissolves in seawater, it forms carbonic acid, which lowers pH. This might suggest difficulty for calcium carbonate secreting organisms, but Devonian ocean chemistry was complex. High temperatures and chemical conditions that differed from today, including different concentrations of magnesium and calcium, allowed robust carbonate production despite elevated carbon dioxide. Alongside stromatoporoids lived tabulate and rugose corals. Tabulate corals formed colonies with a distinctive honeycomb structure, while rugose corals, often called horn corals, were typically solitary and conical. Together, these organisms created three-dimensional structures on the seafloor, providing habitat for countless other species. These reef ecosystems were centers of biodiversity, hosting brachiopods, crinoids, trilobites, and early fishes, among many others. The continental shelves during this period were extensive. Sea levels were high, flooding low-lying areas of the continents and creating broad platforms of shallow water. These epicontinental seas were not marginal environments, but major centers of marine life. The water was warm enough to support high metabolic rates and rapid growth. The sunlight penetrated to the bottom in many areas, allowing photosynthetic organisms to flourish and form the base of complex food webs. Brachiopods, sometimes called lamp shells, were among the most abundant filter feeders in Devonian seas. They attached to hard surfaces or anchored in soft sediment, opening their shells to pass water over specialized feeding structures that captured plankton and organic particles. Different species occupied different niches, some preferring high-energy environments near shore, others thriving in deeper, quieter waters. Their shells are among the most common fossils in Devonian rocks, providing rich data for reconstructing ancient ecosystems. Crinoids, relatives of modern sea stars and sea urchins, were another prominent group. Often called sea lilies because of their plant-like appearance, they consisted of a stem that anchored to the seafloor and a crown of feathery arms that filtered food from the water. Vast crinoid meadows could cover seafloor areas, their waving arms creating underwater forests where other organisms lived and hunted. When crinoids died, their calcite skeletons often broke apart, contributing to limestone formation. Trilobites, iconic arthropods with segmented bodies and hard exoskeletons, were still diverse in the Devonian, though their peak diversity had passed. Different species scavenged on the seafloor, filtered plankton from the water, or hunted smaller prey. Their compound eyes, among the first to evolve in the animal kingdom, allowed sophisticated vision. The variety of trilobite forms, from streamlined swimmers to heavily armoured burrowers, reflects the ecological complexity of Devonian marine environments. The fish fauna of the Devonian was undergoing a major radiation. This period is sometimes called the Age of Fishes, reflecting the diversification of both armoured and unarmoured groups. Placoderms, fish covered in bony plates, dominated many niches, ranging from small filter feeders to massive predators like Dunkleosteus, which could exceed 6 meters in length. Early sharks appeared, their skeletons made of cartilage rather than bone, but their teeth sharp and effective. Lobe-finned fishes, distant relatives of all land vertebrates, swam in both fresh and salt water, their muscular fins hinting at the potential for future terrestrial locomotion. Life on land, during the early to middle Devonian, was sparse compared to the teeming marine ecosystems. Vascular plants had established themselves, but the earliest forests were modest affairs. Plants like Archaeopteris, a tree-like form with fern-like foliage but producing wood, reached heights of perhaps 30 meters, but extensive forests covering vast areas had not yet developed. The soil beneath these plants was thin, the nutrient cycling immature, the ecological complexity low compared to what would come later. Arthropods were the primary terrestrial animals, with early relatives of spiders, mites, and millipedes, exploring the new opportunities on land. Some were predators, others detritivores, feeding on decaying plant matter. Vertebrates had not yet fully transitioned to terrestrial life, though some lobe-finned fishes were beginning to venture into shallow water environments, and perhaps onto mudflats, using their sturdy fins for support. This tentative colonization of land would accelerate, driven by evolutionary innovations that would have consequences far beyond the terrestrial realm. The evolution of forests during the Middle to Late Devonian represents one of the most significant ecological transformations in Earth's history. Before this time, land plants were relatively small, restricted to moist environments, and had limited impacts on their physical surroundings. The development of tree stature, the ability to grow tall and woody, changed everything. Arborescence, the condition of being tree-like, requires several adaptations. A plant must produce rigid tissues, typically wood, to support its weight as it grows taller. It must develop efficient vascular systems to transport water from roots to leaves, and photosynthetic products from leaves to roots. It must anchor itself firmly to withstand wind and storms. These challenges were solved through a combination of anatomical innovations that appeared during the Devonian. The genus Archaeopteris is often considered one of the first true trees. It had a woody trunk that could exceed 1 meter in diameter and reach heights of 30 meters or more. Its branches bore fern-like leaves, though it reproduced via spores rather than seeds. The wood of Archaeopteris shows clear growth rings, indicating seasonal growth patterns, though whether these reflected temperature, moisture, or other environmental factors remains debated. These trees formed the earliest extensive forests, changing the terrestrial landscape from low scrubland to structured multi-story ecosystems. Another important group was the progymnosperms, plants that combined characteristics of ferns and seed plants. They produced wood and grew to tree size, but reproduced with spores. This combination of traits suggests they were transitional forms, evolutionary experiments that would lead to later groups. The appearance of these plants expanded the range of environments that could support substantial vegetation, as they were somewhat less dependent on constant moisture than earlier forms. The development of leaves or leaf-like structures was crucial for efficient photosynthesis. Early vascular plants had simple branching stems that carried out photosynthesis along their length. True leaves, with expanded blade areas supported by veins, allowed much greater surface area for capturing light without proportionally increasing structural support costs. This innovation increased productivity, allowing plants to grow faster and taller, competing more effectively for light. Root systems also underwent major changes during this period. Early plants had simple rhizoids, hair-like structures that anchored them and absorbed water but did not penetrate deeply. As plants grew larger, they needed deeper, more robust root systems to provide stability and access to water during dry periods. The evolution of true roots, structures that could branch and penetrate soil, was as important as the evolution of height above ground. The seed habit, the production of seeds rather than spores, emerged by the Late Devonian, though it would not become dominant until later periods. Seeds offered major advantages over spores. A seed contains an embryo with stored nutrients, protected by a tough coat, allowing it to survive periods of dormancy and germinate when conditions are favourable. Spores, by contrast, are smaller and simpler, relying on external moisture for the early stages of development. The evolution of seeds allowed plants to reproduce successfully in drier environments, expanding their geographic range beyond stream banks and wetlands into uplands and areas with seasonal rainfall. These innovations did not appear simultaneously or in a single lineage. Different plant groups evolved different solutions to the challenges of terrestrial life. Some, like the lycophytes, which would later produce the giant club mosses of the Carboniferous, developed scale-like leaves and hollow trunks. Others, like the progymnosperms and later seed plants, developed true leaves and solid wood. The result was an increasingly diverse terrestrial flora, occupying an expanding range of habitats. The colonization of uplands was particularly significant. Early plants had been restricted to lowlands, areas where water tables remained high and moisture was reliable. As plants developed deeper roots and seeds, they could move into drier, more elevated terrain. These upland areas had weathered rock exposed at the surface, fresh mineral substrates that had not yet been chemically processed by life. The arrival of plants in these environments initiated weathering at rates the planet had never experienced. The structure of forests changed the physical environment in multiple ways. Tree canopies intercepted rainfall, altering how water reached the ground. Roots stabilized soil, reducing erosion in some contexts while increasing it in others through physical disruption of rock. Leaf litter accumulated on the forest floor, beginning the process of building organic rich soils. These changes had local effects on hydrology and soil chemistry, but their cumulative impact, scaled across continents and millions of years, would prove profound. The expansion of forests also affected the carbon cycle. Living trees store carbon in their wood, temporarily removing it from the atmosphere. When trees die, decomposition returns this carbon to the atmosphere as carbon dioxide. But if burial prevents decomposition, the carbon remains sequestered. In wetland environments, where low oxygen levels slow decay, dead plant material could accumulate as peat. Over time, burial and heat could transform peat into coal, permanently locking carbon underground. This process was minor during the Devonian, but would become massive during the Carboniferous. More immediately significant was the effect of roots on weathering. As forests spread, especially into upland areas, They brought with them an army of microscopic agents, bacteria and fungi that formed symbiotic relationships with plant roots. These microbes, along with the roots themselves, released organic acids and other compounds that attacked rock minerals, accelerating chemical breakdown. This acceleration of weathering, more than any other single factor, drove the coming transformation of the Earth's atmosphere and climate. The most profound innovation of the Devonian forests was hidden beneath the ground. While the vertical growth of trees created visible changes to the landscape, the horizontal and downward expansion of root systems initiated chemical processes that would reshape the entire planet. These roots were not simple anchors but complex organs capable of fundamentally altering the interface between rock and water. Early vascular plants had possessed rhizomes and simple root-like structures, but these penetrated only the uppermost layers of soil and weathered rock. The roots of Devonian trees were different in both depth and complexity. They could extend meters into the substrate, following cracks in bedrock, exploiting weaknesses, and physically wedging apart solid stone through their growth. This process, called rhizoturbation, dramatically increased the surface area of rock exposed to chemical weathering. The physical disruption alone was significant. When roots grow into cracks, they exert pressure as they expand. Over time, this pressure can fracture rock, breaking large pieces into smaller fragments. Each fracture creates new surfaces where water can contact mineral grains. The relationship between surface area and reaction rate is fundamental in chemistry. More exposed surface means more sites where chemical reactions can occur, accelerating the transformation of rock into soil. But the physical action of roots was only part of the story. Around each root existed a zone called the rhizosphere, a region of intense biological and chemical activity extending a few millimeters into the surrounding soil. In this zone, roots interacted with countless microorganisms, primarily bacteria and fungi, in relationships ranging from neutral coexistence to intimate symbiosis. These interactions created a chemical environment unlike anything that existed in lifeless soil. Plant roots secrete compounds called exudates, organic molecules that leak or are actively pumped from root cells into the surrounding soil. These exudates include sugars, amino acids, and organic acids such as citric acid, malic acid, and oxalic acid. The organic acids are particularly important for weathering. They contain hydrogen ions that can displace metal ions from mineral structures, effectively dissolving components of rock and releasing them into soil water. Fungi formed mycorrhizal associations with many Devonian plants, partnerships where fungal filaments extended from roots into soil, greatly expanding the plant's effective reach. The fungi absorbed nutrients, particularly phosphorus, and transferred them to the plant in exchange for sugars produced through photosynthesis. In the process of acquiring nutrients, these fungal filaments secreted their own acids and enzymes, adding to the chemical assault on rock minerals. The result of this biological activity was an acceleration of silicate weathering, the primary geological process that removes carbon dioxide from the atmosphere over long timescales. Silicate weathering begins when carbon dioxide dissolves in rainwater, forming carbonic acid. This weak acid reacts with silicate minerals in rocks, breaking them down and releasing metal cations such as calcium, magnesium, and potassium. These cations combine with bicarbonate ions, products of the carbonic acid dissociation, and are carried by rivers to the ocean. In the ocean, marine organisms use calcium and bicarbonate to build shells and skeletons of calcium carbonate. When these organisms die, their remains sink to the seafloor. Over time, burial and lithification transform this material into limestone. The carbon that was once atmospheric carbon dioxide is now locked in solid rock, potentially for hundreds of millions of years, until tectonic processes recycle it through subduction and volcanism. The innovation of deep-rooted plants was that they dramatically accelerated the silicate weathering step of this cycle. Modelling studies suggest that Devonian forests increased weathering efficiency by a factor ranging from 1.64 to 2.39 for a given atmospheric carbon dioxide concentration. This means that for the same amount of carbon dioxide in the atmosphere, the rate at which it was removed and locked into rock increased by more than double in some estimates. The geographic expansion of forests multiplied this effect. As plants colonized upland areas previously devoid of vegetation, they brought their weathering acceleration to fresh rock surfaces that had weathered only slowly through purely physical and chemical processes. Mountain ranges, plateaus, and exposed bedrock across continents became sites of intense chemical activity. The cumulative effect, integrated across millions of years and vast areas, was a massive drawdown of atmospheric carbon dioxide. The mechanism was elegantly simple. More roots meant more rock surface area exposed to weathering. More biological activity meant stronger acids and more aggressive chemical attack. More geographic coverage meant more total area undergoing accelerated weathering. The feedback was powerful and, once initiated, difficult to stop. As long as plants continued to spread and evolve more effective root systems, the weathering acceleration continued, pulling carbon dioxide from the atmosphere at rates that outpaced volcanic and other sources of replenishment. This was not a conscious process, not an intentional engineering of climate by the plants. It was simply the consequence of organisms adapting to terrestrial life, evolving traits that allowed them to access nutrients and water more effectively. The planetary scale consequences were entirely incidental, a side effect of local adaptations that happened to scale into a global transformation. The forests were succeeding at their immediate evolutionary challenges, while inadvertently destabilizing the climate system that had supported marine life for over 100 million years. Understanding how roots consume carbon dioxide requires examining the chemical reactions at the heart of silicate weathering. These reactions are not complex in their basic form, but their global implications are profound. They represent the primary mechanism by which the Earth regulates its own temperature over geological time, a planetary thermostat that operates through the slow transformation of rock. The process begins in the atmosphere. Carbon dioxide gas dissolves in water droplets, whether in clouds, falling rain, or moisture on leaf surfaces. When carbon dioxide dissolves, some molecules react with water to form carbonic acid. The chemical equation is straightforward. Carbon dioxide plus water yields carbonic acid. This is a weak acid, much less corrosive than sulfuric or hydrochloric acid, but given enough time and surface area, it is sufficient to break down even resistant minerals. Carbonic acid dissociates, releasing hydrogen ions and bicarbonate ions. The hydrogen ions are what give the solution its acidic character, its ability to attack other substances. When this acidified water contacts silicate minerals in rocks, the hydrogen ions displace metal ions from the mineral structure. For example, a calcium silicate mineral might react with carbonic acid to yield dissolved calcium ions, dissolved bicarbonate ions, silica, and water. The dissolved calcium and bicarbonate ions are mobile. They move with soil water downward through the soil profile, eventually reaching streams and rivers. The rivers carry this dissolved load to the ocean, where the calcium and bicarbonate can combine to form calcium carbonate, either through direct precipitation or, more commonly, through biological processes, where marine organisms build shells and skeletons. The key point is that carbon which entered the system as atmospheric carbon dioxide exits the system as solid carbonate rock on the seafloor. The carbon is no longer free to act as a greenhouse gas. It is locked in mineral form, removed from the active carbon cycle, until tectonic processes eventually subduct the rock and return the carbon to the atmosphere through volcanic outgassing, a process that takes hundreds of millions of years. The rate of this weathering process depends on several factors. Temperature matters because chemical reactions generally proceed faster at higher temperatures. Rainfall matters because water is the medium in which reactions occur and the transport mechanism for dissolved products. The amount of exposed rock surface matters because reactions occur at surfaces, not within solid mineral grains. And biological activity matters because organisms, particularly plants and their associated microbes, can dramatically accelerate the chemical breakdown of minerals. In the absence of life, silicate weathering proceeds through purely physical and chemical means. Physical weathering, driven by temperature fluctuations, freeze-thaw cycles, and mechanical stress, breaks rocks into smaller pieces, increasing surface area. Chemical weathering occurs as naturally acidified rainwater contacts these surfaces. The process is slow but continuous. Over geological time, mountains erode to plains, and carbon dioxide is gradually consumed. The arrival of plants changed the equation. Roots increased the surface area of rock exposed to water by penetrating into cracks and breaking larger pieces into smaller ones. The organic acids released by roots and associated microbes increased the hydrogen ion concentration in soil water, making it more corrosive than rainwater alone. The biological demand for nutrients meant that organisms actively worked to break down minerals, not passively waiting for chemical equilibrium to be reached. The soil zone became a biogeochemical reactor, a place where biological, geological, and chemical processes interacted synergistically. The depth of this active zone increased as root systems grew deeper. The geographic extent increased as plants colonized new areas. The intensity of chemical activity increased as more aggressive acid-producing organisms evolved. Each of these factors contributed to accelerating the global rate of silicate weathering. The acceleration had limits. The rate cannot increase indefinitely because it depends on the supply of fresh rock, the availability of water, and the kinetics of the chemical reactions themselves. But within these constraints, the Devonian plant expansion represented a major perturbation. The new steady state for silicate weathering was significantly faster than the old one, meaning that for a given rate of volcanic carbon dioxide input, the atmospheric concentration would settle at a lower equilibrium level. This is how life gained leverage over climate. By accelerating a key process in the carbon cycle, plants shifted the balance point of the system. The atmosphere had been in equilibrium at high carbon dioxide concentrations because weathering rates, though slow, matched volcanic input rates. When weathering accelerated, the removal rate exceeded the input rate, and atmospheric carbon dioxide began to decline. The decline would continue until weathering slowed enough, perhaps due to cooling reducing reaction rates, or until volcanic input increased, or until some other factor restored balance at a new, lower atmospheric concentration. The elegance of this mechanism lies in its simplicity. No exotic chemistry is required, no rare elements, no unusual conditions. Just rock, water, carbon dioxide, and life interacting through basic chemical principles. Yet the cumulative effect, integrated over millions of years and planetary scales, is sufficient to shift climate states, end ice ages, or initiate them, and determine whether a planet is habitable or frozen. The Late Devonian forests did not invent silicate weathering. The process had operated throughout Earth's history, regulating climate long before plants existed. What the forest did was accelerate it, tipping the system out of the stable greenhouse state it had maintained for over 100 million years. The consequences of that acceleration would ripple through every ecosystem on the planet, but most severely in the warm, shallow seas where life had flourished during the long, warm period. The quantitative impact of root systems on weathering rates has been estimated through multiple approaches. One method involves comparing modern weathering rates in vegetated versus unvegetated areas. Another uses geochemical models that simulate the carbon cycle and adjust parameters to match evidence from the rock record. A third examines the concentration of weathering products in ancient soils and sediments, inferring the intensity of chemical activity from the degree of mineral alteration. These different approaches converge on a consistent picture. The presence of vascular plants with deep root systems increased the efficiency of silicate weathering by a factor between approximately 1.6 and 2.4. This range reflects uncertainty in the models and the specific conditions being simulated, but the central conclusion is robust. Weathering became substantially faster once forests spread across the continents. To understand what this acceleration means, consider the carbon cycle as a balance between inputs and outputs. Volcanic activity adds carbon dioxide to the atmosphere at a relatively steady rate over millions of years, though individual eruptions are episodic. Weathering removes carbon dioxide at a rate that depends on climate, topography, and biology. If inputs and outputs are equal, atmospheric concentration remains stable. If outputs exceed inputs, concentration declines. If inputs exceed outputs, concentration rises. In the early Paleozoic, the system was balanced at high carbon dioxide levels. Weathering rates, though slower per unit area than they would be in vegetated systems, were sufficient to match volcanic inputs when integrated over the vast timescales involved. The climate was warm, which enhanced weathering through faster reaction kinetics, providing a stabilizing feedback. If carbon dioxide rose, warming increased, weathering accelerated, and carbon dioxide was drawn back down. If carbon dioxide fell, cooling reduced weathering, allowing carbon dioxide to rebuild. The Devonian plant expansion broke this balance. Weathering acceleration meant that even at lower carbon dioxide concentrations, weathering could proceed faster than before. The stabilizing feedback weakened. As carbon dioxide fell and climate cooled, the biological component of weathering remained strong because plants continued to spread and root systems continued to deepen. The output side of the carbon balance increased, while the input side remained roughly constant, driving atmospheric concentration downward. The rate of this decline was not uniform. It depended on how quickly forests spread, which in turn depended on evolutionary innovations and the availability of suitable habitat. The fossil record shows that different plant groups expanded at different times. Progymnosperms like Archaeopteris spread during the Middle Devonian. Seed plants emerged by the Late Devonian. Lycophytes diversified throughout the period. Each expansion event would have contributed to weathering acceleration, adding incremental pressure on atmospheric carbon dioxide. Geographic factors also mattered. Weathering is most effective in humid, mountainous regions, where rainfall is abundant, and topographic relief ensures continuous exposure of fresh rock as erosion removes weathered material. The Late Devonian world had such regions, including mountain ranges formed by tectonic collisions. As plants colonized these areas, they brought their weathering acceleration to environments where physical weathering was already intense, creating zones of particularly rapid carbon dioxide consumption. The mathematical relationship between atmospheric carbon dioxide and weathering rate is nonlinear. Doubling carbon dioxide does not double weathering because the effect saturates at high concentrations. Similarly, the biological acceleration does not scale linearly with plant biomass or root depth. These nonlinearities make precise prediction difficult, but they do not change the fundamental conclusion that a major increase in biological weathering will drive atmospheric carbon dioxide downward. The decline was not instantaneous even on geological timescales. Carbon dioxide concentrations likely took millions of years to fall from their early Devonian peaks to the lower levels characteristic of the Late Devonian. During this time, the climate system was responding, temperatures were falling, ice was beginning to form in high latitudes, and the oceanic and atmospheric circulation patterns were adjusting to the new thermal structure. One crucial aspect of this acceleration is that it was, in a sense, irreversible once it started. Plants did not unevolve their root systems. Forests did not spontaneously retreat from the uplands they had colonized. The biological enhancement of weathering became a permanent feature of the Earth system, even after the initial pulse of expansion. As long as substantial vegetation covered the continents, weathering rates would remain elevated compared to the pre-plant baseline. This permanence meant that the Earth's carbon cycle had fundamentally shifted to a new regime. The old equilibrium, where high carbon dioxide was stable, was no longer attainable without some external forcing, like a massive increase in volcanic activity. The planet had moved into a new domain where lower carbon dioxide was the stable state, where greenhouse conditions required active maintenance through unusually high volcanic input, and where the default tendency was toward cooler climates. The acceleration of weathering is an example of a planetary-scale feedback driven by biological evolution. Life did not passively respond to environmental conditions. It actively modified those conditions in ways that fed back on the physical and chemical systems governing climate. This kind of feedback, where life influences its own environment, is characteristic of the Earth system and distinguishes our planet from lifeless worlds, where only physical and chemical processes operate. The Late Devonian weathering acceleration was not the first time life had influenced climate. Photosynthetic organisms had been oxygenating the atmosphere for billions of years. but it was among the first times that terrestrial life, life outside the oceans, had gained such leverage over the climate system. This leverage would only increase in subsequent periods as forests became more extensive and diverse, and as new groups of organisms evolved new ways to interact with their physical environment. The transformation of the carbon cycle during the Late Devonian left traces in the chemistry of marine rocks. These traces, preserved in limestone and other sedimentary deposits, provide quantitative evidence for the massive shifts in carbon storage and movement between reservoirs. The most important of these traces is the stable carbon isotope ratio, expressed as delta carbon-13. Carbon exists in two stable forms, isotopes that differ in atomic mass but not in chemical behavior. Carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons, making it slightly heavier. Both isotopes occur naturally, with carbon-12 vastly more abundant, making up roughly 99% of all carbon. The ratio between these isotopes seems like a minor detail, but it contains information about biological and geological processes. Photosynthesis discriminates between the two isotopes. The enzymes that fix carbon dioxide during photosynthesis preferentially grab carbon-12 because it is lighter and reacts slightly faster. This means that organic matter, the tissues of plants and other photosynthetic organisms, becomes enriched in carbon-12 relative to the carbon dioxide they absorbed. The remaining atmospheric or dissolved carbon dioxide becomes slightly enriched in carbon-13. When organic matter is buried and removed from the active carbon cycle, it takes its carbon-12 enriched signal with it. The carbon dioxide left in the atmosphere and dissolved in the oceans becomes relatively richer in carbon-13. Marine organisms building shells from this carbon dioxide incorporate the carbon-13 enriched signal into their calcium carbonate skeletons. When these shells are preserved as limestone, they record the isotopic composition of the ocean at the time they formed. A positive delta carbon-13 excursion in marine carbonates indicates that organic carbon was being buried at an elevated rate, removing light carbon and leaving heavy carbon enriched in the surface reservoirs. This is precisely what the Late Devonian rock record shows. Marine limestones from this period exhibit positive excursions in delta carbon-13, with values shifting by up to 4 per mil, a substantial change that requires explanation. The magnitude of the shift reflects the scale of carbon burial. To move the isotopic composition of the entire ocean, which is a massive reservoir, requires burying enormous quantities of organic carbon. This burial must be global, not just a local phenomenon in one basin. The Late Devonian excursions are found in marine sections from multiple continents, confirming that the process was indeed worldwide. The timing of these excursions correlates with other evidence for environmental change. The largest excursions occur during periods when black shales, organic-rich sediments, are being deposited in marine basins. They also correlate with times when carbonate platform sedimentation declines, the so-called carbonate crisis, and they coincide with evidence for glaciation and sea level fall. This convergence of independent lines of evidence strengthens the interpretation that a major perturbation of the carbon cycle was underway. The organic carbon being buried came from two sources. One was terrestrial plant material, swept into rivers and carried to marine basins, where it was buried in sediments. The other was marine organic matter, primarily from algae, which thrived in nutrient-rich waters, but whose remains were preserved when ocean bottoms became anoxic and decomposition was prevented. Both sources contributed carbon-12 enriched material to the sedimentary reservoir, driving the isotopic composition of the remaining ocean toward heavier values. The preservation of organic matter requires special conditions. In oxygenated environments, bacteria and other organisms decompose organic material, returning its carbon to the water as carbon dioxide. For organic matter to be buried and permanently removed from the cycle, it must either be buried so rapidly that decomposition cannot keep up, or it must reach environments where oxygen is absent and decomposition is impossible. The Late Devonian provided both conditions at different times and places. The black shales that characterize much of the Late Devonian marine record are evidence of anoxic conditions. These fine-grained dark sediments are rich in organic carbon, sometimes containing several percent by weight. The darkness comes from the carbon itself and from sulfide minerals that form in oxygen-depleted conditions. The presence of these shales in shallow to moderately deep marine settings indicates that large areas of the seafloor were suffocating, unable to support the organisms that would normally consume and recycle organic debris. The isotopic signal from these shales, when they contain carbonate minerals, confirms the global nature of the carbon burial. The excursions are not artifacts of local conditions, but reflect changes in the global carbon isotope budget. This means the carbon burial was not confined to one ocean basin or one region. It was happening wherever organic-rich sediments were accumulating, which during the Late Devonian was in many places across the planet. The return to more typical isotopic values after the excursions indicates that the intense burial phase eventually ended. As climate and ocean conditions changed, as sea levels shifted, and as ecosystems reorganized, the rates of organic carbon burial declined toward more normal levels. But the carbon that had been buried during the excursion remained locked in the sedimentary record, removed from the atmosphere-ocean system for the foreseeable geological future. The Delta Carbon-13 excursions serve as markers in time, allowing geologists to correlate rocks from different continents and recognize globally synchronous events. They also provide quantitative constraints for models of the carbon cycle, allowing researchers to estimate how much carbon was moved and how quickly. These models, calibrated to match the isotopic and sedimentological evidence, consistently point to a scenario where accelerated weathering and enhanced organic burial acted together to draw down atmospheric carbon dioxide. The black shales of the Late Devonian are among the most distinctive rocks of this period. They occur on multiple continents in sequences that span millions of years, and they record conditions fundamentally different from those that created the limestones and reef rocks of earlier times. These dark, fine-grained sediments are archives of environmental stress, preserving evidence of oxygen depletion and mass mortality in the ancient oceans. The color of these shales comes from their composition. Organic carbon, when present in concentrations of even a few percent, darkens sediment. In the most organic-rich intervals, carbon content can exceed 10%, making the rock appear nearly black. The carbon is finely disseminated, the microscopic remains of algae, bacteria, and other organisms that lived in the water column above, and whose remains settled to the seafloor after death. In oxygenated bottom waters, this organic rain would be consumed by scavengers and decomposed by bacteria, returning nutrients and carbon to the water. Only a small fraction would be buried and preserved. But when bottom waters lose their oxygen, this consumption ceases. The organic matter accumulates undisturbed, building up in sediments at rates much higher than normal. The result is an organic-rich deposit, a black shale, that records a time when the ocean floor could no longer support aerobic life. The formation of black shales requires specific conditions. First, there must be high productivity in surface waters, generating a large flux of organic matter to the seafloor. Second, there must be restricted circulation or sluggish ventilation, preventing the replenishment of oxygen. Third, the rate of organic matter delivery must exceed the rate at which any remaining oxygen can oxidize it. When these conditions align, anoxia develops, and black shales accumulate. The Late Devonian provided these conditions repeatedly. The high nutrient runoff from continents, driven by accelerated weathering and the expansion of terrestrial ecosystems, fertilized coastal waters. Algal blooms erupted, productivity surged, and vast amounts of organic matter rained down to the seafloor. In basins with restricted circulation, either because of their geometry or because of stratification in the water column, oxygen could not be resupplied quickly enough. Anoxia spread. The geographic distribution of these black shales is telling. They occur in both shallow and deep marine settings, from continental shelves to deeper basins. This widespread distribution indicates that anoxia was not confined to isolated restricted basins, but affected broad areas of the ocean. In some cases, the anoxic zone may have extended upward into the water column, creating a stratified ocean where only the surface layer retained oxygen. The most famous of the Late Devonian black shales are the Kellwasser horizons, named after a locality in Germany. These layers mark episodes of particularly intense anoxia around the Frasnian-Furmenian boundary, approximately 372 million years ago. The Kellwasser shales are found across Europe, North America, and other regions, confirming their global significance. They coincide with one of the major extinction pulses of the Late Devonian, suggesting a direct link between ocean anoxia and biological crisis. Later in the Devonian, around 359 million years ago, another set of black shales was deposited. These are associated with the Hagenberg event, the terminal Devonian extinction. The Hagenberg black shale similarly records anoxic conditions, though the exact environmental sequence was more complex, involving oscillations between different water depths and oxygen levels as sea level rose and fell in response to glaciation. The preservation of organic matter in these shales had consequences beyond the immediate recording of anoxia. Each pulse of black shale deposition represented a massive transfer of carbon from the active surface system into long-term geological storage. This burial reduced atmospheric carbon dioxide, not through chemical weathering but through physical sequestration. The carbon in the organic matter came ultimately from atmospheric carbon dioxide, fixed by photosynthesis. By burying this carbon before it could decompose and release its carbon dioxide, the system effectively locked it away. The dual mechanism of carbon dioxide drawdown, chemical weathering on land, and organic burial at sea acted synergistically. Weathering accelerated by plants mobilized nutrients that drove productivity and anoxia. The anoxia allowed efficient burial of organic carbon, which removed carbon dioxide from the atmosphere. Lower carbon dioxide led to cooling, which triggered other changes in ocean circulation and climate that fed back on the system. The black shales are evidence of this complex interconnected chain of cause and effect. In addition to organic carbon, the black shales contain other chemical signatures of anoxic and euxinic conditions. Sulfur isotopes record the activity of sulfate-reducing bacteria, which thrive in oxygen-depleted sediments and produce hydrogen sulfide. Trace metal concentrations reflect the chemistry of the water column, with certain metals like molybdenum and uranium becoming enriched under anoxic conditions. Iron speciation, the distribution of iron among different mineral forms, provides another proxy for oxygen levels. Together, these geochemical indicators paint a detailed picture of the hostile conditions that prevailed. The thickness and extent of black shale deposits also provide clues about the duration and intensity of anoxic episodes. Thick sequences suggest prolonged anoxia lasting thousands to hundreds of thousands of years. Thin layers interbedded with other sediment types indicate briefer anoxic pulses, separated by periods of better oxygenation. The Late Devonian record shows both patterns reflecting the dynamic, oscillating nature of the environmental crisis rather than a single sustained collapse. The weakening of the greenhouse effect did not announce itself with sudden storms or dramatic shifts visible within a human lifetime. Instead, the cooling unfolded across millions of years, a persistent downward trend in global temperatures that gradually transformed the planet's climate state. The warmth that had characterized the early Paleozoic, maintained for over 100 million years, began to dissipate as the atmospheric blanket thinned. Temperature itself is difficult to measure directly in ancient rocks. There are no fossil thermometers, no preserved weather records. Instead, scientists rely on proxies, indirect indicators that respond predictably to temperature changes. Oxygen isotopes in marine fossils provide one such proxy. The ratio of oxygen-18 to oxygen-16 in calcium carbonate shells reflects the temperature of the water in which the organism lived, with cooler waters producing higher ratios of the heavy isotope. Analysis of Late Devonian marine fossils shows a progressive shift toward heavier oxygen isotope values, consistent with cooling ocean temperatures. The magnitude of the shift suggests a decline of several degrees Celsius in tropical sea surface temperatures, with potentially larger changes at higher latitudes. These numbers might seem modest, but even a few degrees of global cooling is sufficient to alter atmospheric circulation patterns, shift precipitation zones, and affect the viability of temperature-sensitive organisms. The cooling was not uniform across all regions or all seasons. Climate models suggest that the most pronounced temperature changes occurred at high latitudes, particularly in the southern hemisphere, where the supercontinent Gondwanaland extended deep into polar regions. Tropical temperatures may have remained relatively warm, though cooler than before, while polar regions experienced much more severe declines, crossing thresholds where seasonal freezing could persist into permanent ice. The distribution of fossil organisms provides another line of evidence for cooling. Warm water species that had thrived across broad latitudinal ranges during the early Devonian became progressively restricted to lower latitudes as the period advanced. Reef-building organisms, particularly sensitive to temperature, showed declining diversity and geographic range. By the Late Devonian, extensive reef systems were confined to tropical regions, whereas earlier they had extended into much higher latitudes. The timing of the cooling correlates with the evidence for accelerated weathering and carbon burial. As plant forests expanded during the Middle Devonian, carbon dioxide levels began their decline. The cooling signal appears shortly afterward in the geological record, with a lag time consistent with the thermal inertia of the ocean system. The ocean contains vastly more heat than the atmosphere, and responds more slowly to changes in radiative forcing, delaying the full expression of cooling even after. Greenhouse gas concentrations have fallen. The rate of cooling varied. There were periods of more rapid temperature decline, and periods where cooling slowed or even reversed temporarily. These fluctuations reflect the complex feedbacks operating in the climate system. When ice sheets began to form, the ice albedo feedback amplified cooling. When ice melted during warmer intervals, this feedback reversed. The carbon cycle itself provided feedbacks, with cooler temperatures slowing weathering rates and potentially allowing carbon dioxide to rebuild slightly, though the biological component of weathering prevented full recovery to earlier levels. Ocean circulation patterns shifted in response to cooling. The temperature gradient between equator and poles drives atmospheric and oceanic circulation. A stronger gradient, with cooler poles and still warm tropics, would have intensified these circulation patterns, potentially increasing wind speeds and ocean current velocities. Changes in circulation affected nutrient distribution, with upwelling zones shifting, and productivity patterns changing in ways that influence marine ecosystems. The atmosphere itself became drier in some regions as cooling reduced evaporation rates. Water vapor, itself a greenhouse gas, declined as temperatures fell, providing an additional feedback that amplified the initial cooling. Precipitation patterns shifted, with some areas becoming wetter and others drier. These regional changes in hydrology affected terrestrial ecosystems, determining which areas could support forest growth and which would remain barren or support only sparse vegetation. Continental interiors, far from the moderating influence of oceans, experienced particularly strong seasonal temperature swings. Summers remained warm, but winters grew colder. In high-latitude regions, winter temperatures eventually dropped below freezing, allowing seasonal snow to accumulate. In some years, not all of this snow melted during the following summer. The residual snow from one year persisted and was buried by new snow the next year, beginning the process of ice sheet formation. The accumulation of ice required specific conditions. Sufficient elevation was needed to ensure cold temperatures year-round. Adequate moisture was necessary to supply snowfall, and the climate had to cool enough that summer melting did not remove all the winter accumulation. As the Late Devonian progressed and carbon dioxide continued to decline, more regions of Gondwanaland met these criteria. The feedback between ice formation and further cooling is powerful. Fresh snow reflects up to 90% of incoming sunlight, far more than rock or vegetation. As ice sheets grew, they increased the planet's overall reflectivity, or albedo, causing more solar energy to be reflected to space rather than absorbed. This reduced the energy available to heat the surface, driving temperatures lower still and allowing ice to expand further. Once initiated, glaciation could become self-reinforcing. The transition from greenhouse to icehouse was not instantaneous, but neither did it take hundreds of millions of years. The bulk of the cooling occurred over perhaps 10 to 20 million years during the Middle to Late Devonian, a rapid shift on geological timescales. For individual organisms, adapted to stable warm conditions over countless generations, even this gradual change represented an existential challenge. Populations could migrate toward the equator, following their preferred temperature range, but this migration compressed species ranges and increased competition for limited warm water habitat. The terrestrial ecosystems that had triggered the cooling continued to thrive, largely unaffected by the temperature decline they had initiated. Most land plants could tolerate cooler conditions better than marine organisms could. The forest continued to expand, roots continued to accelerate weathering, and carbon dioxide continued to decline. The feedback loop between plant expansion and climate cooling had been initiated, and no natural brake existed to stop it until much lower carbon dioxide levels were reached. The first ice sheets of the late Paleozoic ice age formed on Gondwanaland, the massive southern supercontinent that included the land areas that would eventually become South America, Africa, Antarctica, Australia, and India. The geographic position of Gondwanaland, extending deep into high southern latitudes, made it particularly susceptible to ice formation once global temperatures fell sufficiently. The evidence for late Devonian glaciation is physical and unambiguous. Glacial pavements, surfaces of bedrock scoured and polished smooth by the passage of ice sheets, have been identified in multiple locations. These pavements often bear striations, parallel scratches carved by rocks embedded in the base of moving glaciers. The orientation of these striations indicates the direction of ice movement, allowing reconstruction of ice flow patterns from ancient highlands toward lowlands. Tillites, sedimentary rocks composed of unsorted debris ranging from fine clay to large boulders, provide another line of evidence. These deposits form when glaciers melt and drop their load of entrained rock and sediment. The chaotic mixture of particle sizes, unlike the sorted sediments deposited by water or wind, is characteristic of glacial deposition. Late Devonian tillites occur in regions that are now tropical, such as Brazil, but which were positioned in high southern latitudes during the Late Devonian due to the configuration of continents at that time. Perhaps the most distinctive glacial features are drop stones, also called ice-rafted debris. These are angular, often striated cobbles and boulders, found isolated within fine-grained marine sediments. The only plausible mechanism for transporting such large stones far from shore and depositing them in otherwise quiet deep-water environments is by iceberg rafting. The stones were frozen into glacial ice on land, carried out to sea as the ice carved into icebergs, and then dropped to the seafloor as the icebergs melted. The presence of drop stones in late Devonian marine sequences confirms that ice sheets reached the coast and produced icebergs. The geographic distribution of these glacial features spans an enormous area. Evidence has been found in modern-day Brazil, Bolivia, and Peru in South America. In Africa, glacial deposits occur in the Central African Republic and Niger, even in parts of what is now the United States, specifically regions that were positioned differently due to continental drift. There are indications of late Devonian glacial influence. This widespread distribution indicates that the ice sheets were extensive, covering millions of square kilometers. The thickness of ice sheets can be estimated from the magnitude of isostatic depression, the way the weight of ice pushes down the underlying crust. While direct measurement of this depression in ancient rocks is difficult, the scale of the glacial features and the extent of the ice sheets suggest thicknesses of at least several hundred meters, possibly exceeding a kilometer in the thickest central portions. This volume of ice represents an enormous quantity of water withdrawn from the oceans. Ice sheets do not form overnight. The process begins with seasonal snow that fails to melt completely during summer. This residual snow is buried by new snow the following winter, gradually compacting under its own weight. As accumulation continues over decades and centuries, the snow transforms into ice. Once the ice reaches a critical thickness, typically several tens of meters, it begins to flow under its own weight, spreading outward from the accumulation zone. This flow is what creates glacial features like pavements and moraines. The climate conditions required for ice sheet formation are specific. Average annual temperatures must be cold enough that winter snowfall exceeds summer melting. This threshold varies with latitude, elevation, and moisture availability, but generally requires mean annual temperatures below freezing. The Late Devonian cooling pushed temperatures in high southern latitudes across this threshold, initiating ice accumulation. The growth of ice sheets was not continuous. Climate varied on shorter timescales, creating cycles of advance and retreat. During colder intervals, ice sheets expanded, pushing farther from their source areas and lowering global sea level. During warmer intervals, melting exceeded accumulation, ice sheets retreated, and sea level rose. These oscillations, driven by variations in orbital parameters, solar output, volcanic activity, and internal climate dynamics, created a complex pattern of glacial pulses rather than a single sustained glaciation. The duration of the Late Devonian glaciation is not precisely known, but geological evidence suggests it lasted at least several million years, from the later part of the Furmenian stage through the end of the Devonian period. This places it as the first major phase of the much longer Late Paleozoic Ice Age, which would persist through the Carboniferous and into the Permian periods, spanning nearly 100 million years in total. The impact of glaciation extended far beyond the ice-covered regions. The storage of water in ice sheets lowered global sea level, a glacio-eustatic effect that drained shallow continental shelf seas around the world. This sea level fall exposed vast areas of seafloor that had been submerged, sometimes for millions of years, eliminating habitats and forcing marine organisms into smaller, more restricted areas. The stress on marine life was not limited to the regions near the ice sheets, but affected every coastline on the planet. The ice sheets also influenced atmospheric circulation. The presence of high, reflective ice surfaces in southern latitudes altered temperature gradients and wind patterns. Cold air masses flowing off the ice sheets would have created persistent high-pressure systems, affecting storm tracks and precipitation patterns across the southern hemisphere, and potentially influencing climate in the northern hemisphere as well through atmospheric teleconnections. The melting phase of glacial cycles had its own impacts. As ice sheets retreated, meltwater surged into the oceans, raising sea level rapidly in geological terms. This could flood previously exposed coastal plains, creating new shallow marine habitats, but the rate of change often exceeded the ability of ecosystems to adjust. The repeated cycles of sea level rise and fall, each potentially spanning thousands to tens of thousands of years, created chronic instability in coastal environments that persisted throughout the Late Devonian crisis. The locking of water into continental ice sheets had a direct and measurable consequence. Global sea level fell. This phenomenon, called glacio-eustatic sea level change, operates on a simple principle. Water that falls as snow on land and accumulates as ice is removed from the ocean. The more ice that forms, the lower sea level drops. When ice melts, the water returns to the ocean and sea level rises again. The magnitude of Late Devonian sea level fall has been estimated from multiple lines of evidence. The minimum estimate, based on the known extent of glacial deposits and reasonable assumptions about ice thickness, suggests a fall of at least 60 meters. Some researchers argue for larger declines, potentially exceeding 100 meters during the most severe glacial episodes. To put this in perspective, a 100-meter sea level fall is roughly equivalent to the change that would occur if all modern ice sheets on Greenland and Antarctica melted, but in reverse. 60 to 100 meters may not sound dramatic, but the impact depends on seafloor topography. The Late Devonian world featured extensive continental shelves, broad, gently sloping platforms extending from the continents into the ocean. These shelves were shallow, typically less than 200 meters deep, and during times of high sea level, they were submerged, creating vast epicontinental seas. When sea level fell by 60 to 100 meters, enormous areas of these shelves became exposed land. The biological consequences were catastrophic for marine life. The shallow continental shelves were the primary habitats for the diverse reef ecosystems that had characterized the Devonian. Stromatoporoids, corals, brachiopods, and countless other organisms lived in these warm, sunlit waters. When sea level dropped, these habitats simply disappeared. The reefs that had grown on the shelves found themselves high and dry, exposed to air, weathering, and erosion. The geographical scale of habitat loss was staggering. Estimates suggest that the area of shallow marine habitat may have been reduced by as much as half during the maximum regression. Species adapted to specific depths, water temperatures, or substrate types had nowhere to go. Unlike terrestrial organisms that might migrate to follow suitable conditions, sessile marine organisms like corals and stromatoporoids could not move. They died where they sat, their skeletons eroding away or being buried under terrestrial sediments. The erosion of exposed carbonate platforms changed the character of sediment deposition. During high sea level stands, shallow platforms accumulate carbonate sediments, primarily from the shells and skeletons of reef organisms. During low stands, these platforms erode and rivers cut channels across them, carrying terrigenous sediment, sands and muds derived from continental weathering into the remaining marine basins. This shift from carbonate to clastic sedimentation is recorded in the rock layers, marking the transition from shallow marine to more terrestrial-influenced conditions. The concept of a carbonate crisis emerged from observations that carbonate platform sedimentation nearly ceased during the Late Devonian, particularly during the Furmenian stage. Instead of thick sequences of reef limestone, the rock record shows thin, discontinuous carbonate layers interspersed with shales and sandstones. This change reflects not just the loss of reef organisms through extinction, but also the physical loss of the environments where carbonate production occurred. In some regions, the exposed shelves became sites of terrestrial sediment deposition. Rivers flowing across newly emergent land deposited gravels, sands, and muds. In arid regions, evaporate minerals like gypsum and halite precipitated as shallow marine embayments evaporated, leaving behind flat salt pans. These deposits, preserved in the rock record, provide direct evidence that areas formerly underwater had become subaerial, exposed to atmosphere and sun. The timing of the regression is constrained by its relationship to other events. The major sea level fall occurred during the later part of the Furmenian stage, culminating in the Hagenberg event at the very end of the Devonian. This timing coincides with evidence for maximum glaciation and with the peak of extinction intensity. The correlation strongly suggests that the physical destruction of habitat through sea level fall was a primary driver of the terminal Devonian extinction. The pattern was not a simple fall and recovery. Instead, the Late Devonian experienced multiple cycles of regression and transgression, sea level falling and rising again, each time by tens of meters. These cycles reflected the waxing and waning of ice sheets in response to climate variations. Each cycle stressed marine ecosystems, forcing them to adjust to new conditions, only to have those conditions change again before full recovery could occur. Some marine organisms could potentially survive a regression by migrating basinward, following the retreating shoreline into deeper water. But this strategy had limits. Deep water environments differ from shallow ones in temperature, light availability, substrate type, and water chemistry. Species adapted to shallow conditions often could not survive in deep water. Moreover, as all the shallow adapted species compressed into smaller remaining areas of suitable habitat, competition intensified and food resources became strained. The exposed platforms themselves became agents of environmental stress. Weathering of carbonate rocks consumes carbon dioxide, but when these rocks are subaerially exposed and actively eroding, they release dust and dissolved ions into rivers and eventually into the ocean. This influx could alter ocean chemistry, affecting calcification rates and potentially stressing organisms trying to build calcium carbonate skeletons. The feedback between physical environmental change and chemical perturbation compounded the stress. The return of high sea level during transgressive phases did not immediately restore ecosystems. The transgression flooded previously exposed land, creating shallow marine habitat, but the organisms that would have colonized this habitat had been decimated during the low stand. Recovery required time for surviving populations to expand and for evolutionary innovation to fill empty ecological niches. In the Late Devonian, each transgression was followed by another regression before complete recovery could occur, maintaining chronic instability. The same root systems that accelerated silicate weathering and drew down atmospheric carbon dioxide had another consequence, one that would prove equally devastating to marine ecosystems. As roots penetrated rock and organic acids, dissolved minerals, essential nutrients locked in continental rocks were mobilized and carried by rivers into the ocean. Among these nutrients, phosphorus would play the most critical role in the coming crisis. Phosphorus is an essential element for all life. It is a key component of DNA, RNA, ATP, and cell membranes. Unlike nitrogen, which can be fixed from atmospheric gas by certain bacteria, phosphorus must be obtained from the environment in mineral form. In most marine ecosystems, phosphorus is the limiting nutrient, meaning that biological productivity is constrained by phosphorus availability. When phosphorus is scarce, productivity remains low. When phosphorus becomes abundant, productivity can explode. In the pre-Devonian world, phosphorus weathering from continents proceeded slowly. Physical weathering of phosphate-bearing minerals occurred, and some dissolution happened through purely chemical processes, but the rates were limited by the lack of biological acceleration. Rivers carried dissolved and particulate phosphorus to the ocean, but the flux was relatively steady and modest. Marine ecosystems had adapted to this baseline nutrient supply, with productivity tuned to available resources. The expansion of vascular plants with deep root systems changed this balance fundamentally. Roots and their associated fungi specifically target phosphorus-bearing minerals because phosphorus is essential for plant growth. The organic acids released by roots are particularly effective at dissolving apatite, the primary phosphorus mineral in rocks. As weathering rates increased overall, phosphorus weathering increased disproportionately because it was being actively mined by organisms that needed it. The magnitude of this increase can be estimated from models of the phosphorus cycle. Some estimates suggest that riverine phosphorus delivery to the ocean may have doubled or even tripled during the peak of the Late Devonian plant expansion. This represents an enormous perturbation to marine nutrient budgets, comparable in relative magnitude to the carbon dioxide drawdown and with similarly profound consequences. The phosphorus reached the ocean dissolved in river water or attached to sediment particles. In coastal waters, where river influence is strongest, phosphorus concentrations rose first. Marine phytoplankton, microscopic algae floating in the sunlit surface waters, responded immediately. Freed from phosphorus limitation, these organisms bloomed, multiplying rapidly and consuming available carbon dioxide and other nutrients. The water turned green or brown with dense algal populations. Algal blooms are natural phenomena, but the scale and frequency of Late Devonian blooms were unusual. Normally, blooms are self-limiting. As algae consume nutrients, concentrations decline and growth slows. But when nutrient delivery is sustained, as it was with the constant runoff from weathering continents, blooms could persist for extended periods, covering vast areas of ocean surface with dense mats of photosynthetic organisms. The geographic pattern of nutrient delivery mattered. River mouths and coastal zones received the highest nutrient loads. In these areas, eutrophication, the over-fertilization of water, would have been most intense, but ocean currents carry dissolved nutrients far from their sources. Upwelling zones where deep water rich in nutrients rises to the surface would have been particularly productive. The combination of upwelled deep nutrients and new terrestrial nutrients created conditions for extreme productivity in certain regions. The composition of the algal communities may have shifted in response to nutrient enrichment. Different species of phytoplankton have different nutrient requirements and tolerances. Some species thrive in nutrient-poor conditions, while others dominate when nutrients are abundant. The species that bloomed during eutrophication pulses may have been different from the typical phytoplankton communities, potentially including forms that are less nutritious for grazers or that produce toxins. The productivity spike while initially seeming beneficial as it would increase food availability for marine animals, carried a hidden cost. All those algae, trillions upon trillions of individual cells, were living, growing, and eventually dying. When they died, their organic matter sank, drifting down through the water column toward the seafloor. This organic rain, vastly increased from normal levels, would become the agent of suffocation for the deep ocean. The timing of nutrient pulses may have been episodic rather than constant. Weathering rates depend on climate, particularly on rainfall. During wetter intervals, more weathering products would be flushed to the ocean. During drier intervals, delivery might slow. This variability would have created pulses of eutrophication, each triggering an algal bloom, each followed by a period of organic matter decomposition and oxygen depletion. The repeated nature of these pulses added to their cumulative impact. The mobilization of nutrients also included other elements besides phosphorus. Nitrogen in various forms, iron, silica, and trace elements all increased in riverine delivery. Each played a role in marine productivity. Iron, for example, is essential for photosynthesis and is the limiting nutrient in some ocean regions today. Increased iron delivery during the Devonian may have fertilized previously iron-limited areas, extending the geographic range of eutrophication. The terrestrial plants driving this nutrient flood were not harmed by it. They continued to thrive, spreading across continents and evolving new forms. The forests were succeeding at the evolutionary challenge of terrestrial life accessing nutrients from rocks, growing tall to compete for light, and reproducing effectively. They had no connection to the distant ocean, no way to sense or respond to the crisis they were triggering. The separation between terrestrial and marine realms meant that success in one could proceed unchecked, even as it generated catastrophe in the other. The arrival of excess nutrients in coastal waters initiated a cascade of biological responses. Eutrophication is the term for this over-enrichment, a process that transforms aquatic ecosystems from nutrient-limited to nutrient-saturated states. In modern times, eutrophication is typically associated with human activities, agricultural runoff and sewage discharge, but the Late Devonian experienced naturally driven eutrophication on a scale never before seen in Earth history. The first organisms to respond were always the phytoplankton, the microscopic photosynthetic organisms forming the base of marine food webs. These included cyanobacteria, green algae, and various other single-celled forms. Under normal conditions, their populations are kept in check by nutrient scarcity. They grow, reproduce, and are consumed by grazers at rates that balance each other, maintaining relatively stable population levels. When nutrients flood in, this balance breaks. Population growth in algae is exponential when resources are unlimited. A single cell divides into two, those two into four, four into eight, and so on. Under ideal conditions, some species can double their population in less than a day. When an entire coastal region receives sustained nutrient input, the multiplication of algal cells becomes staggering. What was clear water becomes turbid, thick with suspended organisms. The color shifts from blue to green, brown, or even red depending on the dominant species. These blooms blocked sunlight from penetrating deeper into the water column. Organisms living below the bloom layer, including other photosynthetic species and the animals that depended on them, found themselves in darkness. This shading effect extended the impact of the bloom beyond the surface, affecting the entire vertical structure of the ecosystem. Deeper-dwelling photosynthetic organisms, unable to access sufficient light, declined or died, further concentrating productivity at the very surface. The oxygen dynamics within the bloom itself were complex. During daylight hours, photosynthesis produced oxygen, sometimes supersaturating surface waters. But at night, photosynthesis stopped while respiration continued. The dense algal populations consumed oxygen through their own respiration, potentially drawing concentrations down significantly. These daily swings in oxygen availability stressed animals trying to live within or below the bloom. Zooplankton, tiny animals that feed on phytoplankton, might be expected to increase in response to the abundant food supply. To some extent they did, but their population growth could not keep pace with the algal bloom. Zooplankton reproduced more slowly than algae, and predators above them in the food web limited their numbers. The result was that grazing pressure remained insufficient to control the bloom, allowing algal populations to reach levels far beyond what could be sustained by grazing alone. The chemical composition of the water changed during blooms. The rapid uptake of nutrients by algae could temporarily deplete surface concentrations, even as continued river input maintained supply. Carbon dioxide was consumed rapidly during photosynthesis, potentially raising pH during daylight hours. This alkalinity shift affected chemical equilibria, including the solubility of calcium carbonate, potentially impacting calcifying organisms like corals and brachiopods trying to build their shells. The duration of individual blooms varied. Some might persist for weeks, others for months, depending on nutrient supply, temperature, and other factors. But in the Late Devonian, the sustained nature of nutrient input from weathering continents meant that blooms could recur frequently, creating nearly continuous eutrophic conditions in coastal waters. The ocean shifted from a state where productivity was naturally regulated to one where it was artificially elevated and unstable. The composition of organic matter produced during blooms mattered for what happened next. Different algal species produce organic compounds with different chemical properties. Some are relatively labile, easily decomposed by bacteria. Others are more refractory, resistant to breakdown. The mix of species in Late Devonian blooms determined how quickly the organic matter would be consumed once it sank, which in turn affected how deeply oxygen depletion would penetrate into the water column. The geographic extent of eutrophication is difficult to determine precisely, but it must have been substantial. Rivers enter the ocean at countless points along coastlines, each carrying its load of weathering products. Ocean currents distribute these nutrients along coasts and into the open ocean. The black shale deposits characteristic of the Late Devonian are found globally, suggesting that the productivity and subsequent anoxia were not limited to a few local basins, but affected wide areas. Some regions may have experienced eutrophication more severely than others. Areas with restricted water circulation, semi-enclosed basins or embayments, would have been particularly susceptible. In these settings, nutrient-rich water could accumulate without being flushed out by ocean currents, creating persistent hotspots of extreme productivity. The geological record suggests that many such restricted basins existed during the Late Devonian, their configurations influenced by tectonic activity and sea level changes. The ecological consequences extended beyond simple changes in productivity. The composition of marine communities shifted towards species tolerant of eutrophic conditions. Opportunistic species, those capable of rapid reproduction and tolerant of variable conditions, thrived. Specialized species, particularly those adapted to stable, oligotrophic conditions, declined. This shift in community structure reduced overall diversity, even in areas where total biomass might have temporarily increased. When the algal blooms died, their legacy sank. The organic matter that had been produced in such abundance at the surface began its descent through the water column, a continuous rain of dead cells and fecal pellets from the zooplankton that had fed on them. This organic rain is a normal feature of ocean ecosystems, but the magnitude during Late Devonian eutrophication events was anything but normal. Decomposition is an oxygen-consuming process. Bacteria break down organic matter, using dissolved oxygen to metabolize the carbon compounds and releasing carbon dioxide as a waste product. Under typical conditions, the rate of organic matter delivery to deeper waters is slow enough that ocean circulation can replenish the oxygen consumed during decomposition. The system remains in balance, with oxygen concentrations staying high enough to support animal life throughout the water column. But when organic matter delivery increases dramatically, as it did during Late Devonian eutrophication pulses, the balance breaks. Bacteria populations exploded in response to the abundant food supply. Their collective respiration consumed oxygen faster than water circulation could replace it. Dissolved oxygen concentrations began to fall, first in deeper waters where circulation was already sluggish, then progressively upward through the water column, as the oxygen demand exceeded supply. The threshold between oxygenated and anoxic conditions is not a single fixed value. Different organisms have different oxygen requirements. Large active animals like fish require relatively high oxygen concentrations to support their metabolic needs. Smaller, less active organisms can survive at lower concentrations, but below approximately 2 milliliters of oxygen per liter of seawater, most multicellular animals struggle to survive. This condition is called hypoxia, low oxygen, and it represents severe physiological stress. As oxygen concentrations continued to fall, zones of true anoxia developed. In these waters, dissolved oxygen reached zero. No animals requiring oxygen could survive. The only organisms that could function were anaerobic bacteria, forms that use chemical pathways not dependent on oxygen. These bacteria continued to decompose organic matter, but they used alternative electron acceptors, including sulfate, one of the abundant ions dissolved in seawater. Sulfate-reducing bacteria produce hydrogen sulfide as a waste product. This compound is highly toxic to most forms of life, even at low concentrations. It interferes with cellular respiration by blocking the enzymes involved in oxygen utilization. When hydrogen sulfide concentrations build up in seawater, the condition is called euxemia. Euxinic waters are not merely devoid of oxygen, but actively poisonous, suffocating, and chemically attacking any organisms that cannot escape. The development of euxemia required specific conditions. Sufficient organic matter delivery was necessary to consume all available oxygen and support sulfate reduction. Restricted water circulation was needed to prevent the hydrogen sulfide from being diluted or oxidized by mixing with oxygenated waters from above. The Late Devonian Ocean, with its complex basin geometry, influenced by sea level changes and continental configuration, provided these conditions in multiple locations. The vertical structure of the water column during anoxic events could be stratified into distinct layers. At the surface, oxygenated water remained, maintained by atmospheric exchange and photosynthetic oxygen production during daylight. Below this, a transition zone existed where oxygen declined gradually. Deeper still, true anoxia prevailed, and in the most extreme cases, euxinic conditions developed near the seafloor, or even extending upward into the water column. The boundary between oxygenated and anoxic water, called a chemocline, could be remarkably sharp, sometimes occurring over just a few meters of depth. Organisms attempting to migrate vertically to find food or avoid predators could cross from habitable water into lethal conditions with little warning. For bottom-dwelling organisms with limited mobility, there was no escape at all. When the anoxic boundary descended to the seafloor, they simply suffocated where they lived. The geographic extent of anoxia varied over time. During the most severe eutrophication pulses, anoxic zones expanded, covering larger areas of the seafloor and potentially merging into continuous regions of oxygen depletion. During intervals when nutrient input slowed or when ocean circulation strengthened, anoxic zones could shrink or disappear, allowing partial recovery of benthic communities. The Late Devonian was characterized by repeated cycles of anoxia development and retreat, each cycle stressing ecosystems that had not fully recovered from the previous event. The preservation of organic rich sediments, the black shales, required these anoxic conditions. In oxygenated bottom waters, the organic matter that reached the seafloor would be consumed by scavengers and burrowing organisms, or decomposed by aerobic bacteria in the sediment. Very little would be permanently buried, but in anoxic conditions, these consumption processes ceased. The organic matter accumulated undisturbed, building up in sediments at concentrations far exceeding those found in normal marine deposits. The colour of these sediments came partly from the organic carbon itself, but also from iron sulfide minerals, particularly pyrite, that formed in the anoxic sediments. When hydrogen sulfide encountered dissolved iron in sediment-poor waters, chemical reactions produced iron sulfide, which precipitated as tiny crystals. These dark minerals, combined with the black organic matter, gave the sediments their characteristic appearance. The presence of pyrite in ancient rocks serves as a diagnostic indicator of euxinic depositional conditions. The duration of individual anoxic events is difficult to determine precisely, but the thickness of black shale sequences provides some constraints. Some layers are only centimetres thick, suggesting brief anoxic episodes lasting perhaps centuries to millennia. Others are metres thick, indicating sustained oxygen depletion over tens or hundreds of thousands of years. The Late Devonian includes examples of both, reflecting variability in the intensity and persistence of the driving mechanisms. The impact on marine life was catastrophic. Benthic communities, organisms living on or in the seafloor sediments, were particularly vulnerable. These included brachiopods, burrowing worms, bottom-feeding arthropods, and many others. When anoxia reached the seafloor, these communities were eliminated. The fossil record shows intervals where diverse bottom-dwelling faunas are abruptly replaced by barren black shales, recording moments when entire seafloor ecosystems suffocated. Mobile organisms could potentially flee ahead of advancing anoxic zones, but their options were limited. Moving into shallower water brought them into zones of intense eutrophication, and possibly into ranges of temperature or salinity they could not tolerate. Moving into deeper water often meant moving into more severe anoxia. The compression of habitable space into narrow zones of acceptable conditions created ecological bottlenecks, where competition intensified and survival became increasingly difficult. The cycles of anoxia recurred throughout the Late Devonian, but two episodes stand out in the geological record for their severity and global extent. The first was associated with the Kellwasser Event, around 372 million years ago. The second was part of the Hangenberg crisis, at the end of the Devonian, approximately 359 million years ago. These episodes, recorded in black shales deposited across multiple continents, represent the most intense phases of marine suffocation during the entire crisis period. Around 372 million years ago, the crisis that had been building throughout the Middle and Late Devonian reached a first major crescendo. This episode, known as the Kellwasser Event after a locality in Germany, where it was first studied in detail, marks the boundary between the Frasnian and Furmenian stages of the Late Devonian. It was not the final extinction pulse of the period, but it was severe enough to fundamentally alter marine ecosystems. The name Kellwasser originally referred to dark limestone layers found interbedded within lighter reef limestones. These dark layers, enriched in organic matter, represented brief intervals when carbonate production by reef organisms was disrupted and replaced by deposition of organic-rich sediment. As geologists studied Late Devonian sections around the world, they found similar organic-rich layers at approximately the same stratigraphic position, suggesting a globally synchronous event. Two distinct pulses of black shale deposition characterize the Kellwasser Event, often called the lower and upper Kellwasser horizons. These represent two separate but closely spaced episodes of marine anoxia, each lasting perhaps tens to hundreds of thousands of years, separated by a brief interval of partial recovery. The double-pulsed nature of the event added to its severity, as organisms that survived the first pulse faced a second assault before full recovery could occur. The carbon isotope record shows positive excursions during the Kellwasser Event, confirming that massive organic carbon burial was occurring. The magnitude of the excursion indicates a major perturbation to the global carbon cycle, with organic matter being removed from the active system and locked in sediments at rates far exceeding background levels. This burial contributed to the ongoing drawdown of atmospheric carbon dioxide, linking the anoxia events to the broader climate cooling trend. The geographic distribution of Kellwasser black shales is remarkable. They appear in Europe, North America, North Africa, and Australia, demonstrating that anoxia affected multiple ocean basins simultaneously. Some sections show black shales in deep basins, as might be expected, but others occur in what were relatively shallow shelf environments. This suggests that oxygen depletion was not confined to isolated deep basins, but affected broad areas of the ocean, including productive shelf seas. The extinction toll was substantial. Reef-building organisms were particularly hard hit. Stromatoporoids, which had dominated reef construction for much of the Devonian, suffered severe declines. Many genera went extinct, and the survivors were diminished in abundance and diversity. Rugose and tabulate corals also declined, with extinction rates exceeding 50% of genera in some groups. The three-dimensional reef structures that had characterized Devonian shelf seas became rare. Planktonic organisms, those living in the water column, also experienced significant losses. Certain groups of tentaculatids, cone-shaped fossils of uncertain biological affinity, but probably planktonic, nearly disappeared. Some ammonoid groups, swimming cephalopods, related to modern nautiluses, went extinct. The loss of planktonic species suggests that anoxia extended upward into the water column, not just affecting the bottom but creating inhospitable conditions through significant vertical extent. Brachiopods, the lampshells that had been among the most abundant filter feeders in Devonian seas, showed varied responses. Some groups that lived in shallow, well-oxygenated environments survived relatively well, though with reduced diversity. Others, particularly those adapted to deeper shelf environments where anoxia was most severe, suffered heavy extinctions. The pattern suggests that ecological preference, particularly depth distribution, determined which groups would survive. The mechanism behind the Kellwasser anoxia fits within the broader framework of eutrophication and organic matter decomposition. Enhanced nutrient delivery from weathering continents drove productivity pulses. The resulting algal blooms produced massive quantities of organic matter. When this material decomposed, oxygen was consumed, and anoxia developed. The two pulses of the Kellwasser event may reflect two particularly intense eutrophication episodes, possibly linked to especially wet climate intervals that accelerated weathering and nutrient delivery. The temperature during the Kellwasser event remains somewhat uncertain. Some evidence suggests cooling had already begun, contributing to stress on warm-adapted organisms. Other evidence indicates relatively warm conditions persisted, possibly even warming briefly during the event itself. This apparent contradiction might be resolved if different regions experience different temperature trends, or if the event occurred during a complex climate transition with rapid fluctuations rather than a simple cooling trend. The recovery after the Kellwasser event was incomplete. Marine diversity rebounded somewhat in the interval between the Kellwasser and the terminal Hangenberg event, but it never returned to pre-crisis levels. Reef ecosystems in particular remained suppressed. The carbonate platforms that had been vibrant centres of biodiversity became muted, with scattered coral growth but lacking the massive framework structures that had existed before. The ocean had shifted to a new, less diverse state. The Kellwasser event serves as a preview of what would come at the end of the Devonian. It demonstrated that the combination of anoxia, nutrient stress, and possibly cooling was sufficient to cause mass extinction. It showed that the crisis was not a singular catastrophe, but a prolonged series of pulses, each capable of eliminating substantial proportions of marine life, and it revealed that recovery between pulses was insufficient to restore ecosystems to their former complexity before the next assault arrived. The preserved black shales from this event have become important archives for studying ancient ocean chemistry and climate. They contain not just organic carbon, but also pyrite, trace metals, and organic molecules that preserve information about the organisms that lived and died during the crisis. Modern analytical techniques allow extraction of increasingly detailed information from these rocks, continually refining our understanding of exactly what happened during those critical hundreds of thousands of years. The Kellwasser event also affected terrestrial ecosystems, though the evidence is less clear than for marine systems. Some plant groups show turnover, with certain species disappearing and being replaced by others. But the terrestrial extinction was far less severe than the marine extinction, consistent with the hypothesis that the primary drivers, eutrophication and anoxia, were marine phenomena. Land plants continued their expansion, roots continued to accelerate weathering, and the fundamental driver of the crisis, the carbon dioxide drawdown, continued unabated. Approximately 13 million years after the Kellwasser event, the Devonian period ended with a crisis even more severe. The Hagenberg Event, named after a locality in Germany where distinctive sediments mark this boundary, represents the terminal extinction of the Devonian, the final pulse that brought the period to a close and initiated the Carboniferous. This event combined all the stresses that had been accumulating throughout the Late Devonian into a concentrated interval of environmental catastrophe. The sequence of events during the Hagenberg crisis unfolded in stages, each adding its own stress to already beleaguered ecosystems. The first stage involved a marine transgression, a rise in sea level that flooded coastal areas and expanded shallow marine habitats. Normally, such a transgression might seem beneficial, increasing available habitat, but in this case it set the stage for renewed anoxia. Following the transgression came the deposition of the Hagenberg Black Shale, recording a pulse of marine oxygen depletion similar to the Kellwasser events, but occurring in a different environmental context. The Black Shale contains high concentrations of organic carbon and shows geochemical signatures of euxinic conditions. This anoxic pulse may have been triggered by the same mechanisms as earlier events: nutrient-driven eutrophication and subsequent organic matter, decomposition consuming dissolved oxygen. But the Hagenberg crisis did not end with this anoxic pulse. Instead, the climate shifted dramatically toward maximum cooling. This was the most severe cold interval of the Late Devonian, the moment when glaciation reached its maximum extent on Gondwanaland. Ice sheets expanded to their largest areas, locking up vast quantities of water and driving a major glacio-eustatic regression, a fall in global sea level. The magnitude of this sea level fall may have exceeded 100 meters, based on evidence from Morocco and other regions. This represents the draining of enormous areas of continental shelf, habitats that had existed for millions of years, reefs that had survived the earlier Kellwasser crisis, found themselves high above the waterline, exposed to air and weathering. The physical destruction of habitat through sea level fall became the dominant stress during this phase. The timing of extinctions within the Hagenberg sequence is crucial for understanding causation. Detailed stratigraphic work shows that the major pulse of extinction did not occur at the beginning of the crisis during the initial transgression, nor during the Black Shale deposition. Instead, it occurred during the subsequent regression as sea level fell and shallow marine habitats were eliminated. This timing strongly implicates habitat loss as the killing mechanism for this particular extinction pulse. The victims of the Hagenberg event included many groups that had survived the Kellwasser crisis. Stromatoporoids, already diminished after the Kellwasser, essentially disappeared. They did not go completely extinct. A few forms survived into the Carboniferous, but they never again achieved the ecological dominance they had enjoyed during the Devonian. The great reef-building organisms of the Paleozoic were gone, and it would be tens of millions of years before other groups evolved to fill their role. Ammonoids suffered catastrophically. These swimming cephalopods, with their coiled shells and complex suture patterns, had diversified into numerous families during the Devonian. The Hagenberg crisis eliminated 86% of ammonoid genera and 87% of species. Only a single family survived into the Carboniferous, though this lone survivor group would eventually rediversify to fill the oceans once again. Deep-water brachiopod communities were completely eliminated. These organisms, which had adapted to live in the quieter, deeper parts of the shelf, could not survive the combination of anoxia and the subsequent loss of habitat. Certain families that had been common throughout the Devonian simply do not appear in Carboniferous rocks. The extinction was absolute, not merely a reduction in abundance, but total elimination of entire evolutionary lineages. Rugose corals, though not as dominant as stromatoporoids, also experienced severe turnover. Many Devonian families disappeared, replaced by new forms that would characterize Carboniferous reefs. The ecological structure of reef communities changed fundamentally. The Devonian reef, with its massive stromatoporoid frameworks and associated diverse fauna, was replaced by a simpler Carboniferous reef, often dominated by crinoids and bryozoans rather than framework-building organisms. The terrestrial realm experienced its own changes, though again less severe than the marine catastrophes. Plant communities showed turnover, with some characteristic Devonian groups declining, and early forms that would dominate the Carboniferous appearing. The first extensive seed plant forests may have emerged around this time, taking advantage of the ecological disruption to colonize new areas. Terrestrial arthropods also showed some extinction, but overall terrestrial diversity was less affected. The cause of the Hagenberg crisis is best understood as a convergence of multiple stressors operating simultaneously. The anoxia pulse stressed marine life through suffocation and toxic conditions. The subsequent extreme cooling stressed warm-adapted organisms through temperature decline. The massive regression physically destroyed habitats and compressed remaining populations into smaller areas. No single cause was responsible. Rather, the combination of all three occurring in rapid succession overwhelmed the capacity of ecosystems to adapt. The climate oscillations during the Hagenberg event were particularly severe. The cooling was not gradual but rapid on geological timescales, possibly occurring over just hundreds of thousands of years. This rate exceeded the capacity of many species to adapt through evolution or to migrate to more favorable environments. The geographic compression of suitable habitat meant there was nowhere to go. The tropical refugia where organisms might normally retreat during cooling were themselves affected by sea level fall and anoxia. The end of the Hagenberg crisis is marked by another transgression, sea level rising again as the glaciers began to melt. This transgression flooded the previously exposed shelves, creating new shallow marine habitat. But the organisms that would have colonized this habitat were gone. The diverse Devonian fauna had been eliminated, and the spaces they had occupied now stood empty, waiting for survivors and newly evolving forms to fill them during the subsequent Carboniferous recovery. The rock record of the Hagenberg event shows sharp transitions. Below the crisis interval, limestones contain abundant fossils of diverse marine organisms. Within the crisis interval, black shales contain few fossils, recording the anoxic pulse. Above the crisis interval, sediments initially show low diversity, dominated by small, simple organisms, opportunistic forms that could colonize disturbed environments. Only higher in the section does diversity gradually rebuild, marking the slow recovery of Carboniferous ecosystems. The Late Devonian extinctions eliminated an estimated 70 to 80% of all animal species over the course of approximately 25 million years. This loss was not evenly distributed across all groups or all environments. The pattern of survival and extinction reveals much about the nature of the crisis, and why some organisms succumbed while others persisted. Stromatoporoids stand as perhaps the most emblematic victims of the Late Devonian crisis. These organisms had been the primary reef builders for much of the Paleozoic, constructing massive framework structures that dominated shallow tropical seas. Their extinction represents not just the loss of individual species, but the collapse of an entire ecological architecture. The Devonian reef ecosystem, defined by stromatoporoid frameworks, disappeared and would not be fully replaced until much later in Earth history. The biological nature of stromatoporoids has been debated. Traditionally classified as sponges based on their porous skeleton structure, their exact affinity remains somewhat uncertain. What is clear is that they secreted calcium carbonate skeletons with distinctive layered structure, and that they were adapted to warm, shallow, well-lit waters. These habitat requirements proved to be vulnerabilities when conditions changed. As waters cooled, became anoxic, and habitats drained, stromatoporoids had nowhere to retreat. Rugose corals, the horn corals, and colonial forms that had partnered with stromatoporoids in reef construction also suffered heavily, though not quite as catastrophically. Many families went extinct, particularly during the Hagenberg event. The survivors into the Carboniferous were diminished in diversity and never regained the abundance they had enjoyed during the Devonian. The ecological role of corals in reef building was substantially reduced in the post-Devonian world. Tabulate corals, colonial forms that created distinctive honeycomb structures, experienced similar fates. These had been common in Devonian reefs, providing structural complexity and habitat for other organisms. Their decline mirrored that of stromatoporoids and rugose corals, reflecting the vulnerability of the entire reef ecosystem to the combined stresses of anoxia, cooling, and habitat loss. The Carboniferous would see new forms emerge, but the classic Devonian reef assemblage was gone. Ammonoids, the coiled shell cephalopods that swam in the open ocean, faced repeated near extinction. During the Kellwasser Event, many families disappeared. During the Hagenberg crisis, the attrition was even more severe, with only one family surviving the end of the Devonian. This extreme bottleneck created a genetic and ecological crisis for the group. The surviving family, representing perhaps just a handful of species, carried the entire future of ammonoid diversity forward into the Carboniferous. The pattern of ammonoid extinction suggests they were vulnerable to both anoxia and ecological disruption. As swimming organisms, they could move to avoid local anoxic zones, but if anoxia became widespread, they would eventually encounter lethal conditions. As predators or scavengers, they depended on food webs that were themselves collapsing. The cascading effects of ecosystem disruption propagated upward through trophic levels, affecting even mobile, relatively sophisticated organisms. Brachiopods, the lampshells that had been extraordinarily diverse in Devonian seas, showed differential survival based on their habitat preferences. Shallow water forms that lived in well-circulated environments had higher survival rates. Deep water forms, particularly those adapted to quiet basins with fine sediments, were hit hardest. This pattern aligns with the mechanism of oxygen depletion, affecting deeper and more restricted waters most severely. The organisms living in precisely those zones most vulnerable to anoxia were the ones that went extinct. Certain groups of brachiopods disappeared entirely. The Eutropids, a diverse and long-lived order that had thrived throughout the early Paleozoic, were completely eliminated during the Late Devonian crisis. Their extinction removed an entire major evolutionary lineage, one that had existed for over 150 million years. The loss demonstrates that even groups with long histories of success and broad geographic distribution could be vulnerable when environmental change was sufficiently severe. Trilobites, though not as affected as reef-dwelling organisms, still suffered declines. These armoured arthropods had been in slow decline since their peak diversity in the Cambrian and Ordovician periods, but the Late Devonian accelerated that decline. Many families disappeared, and the ecological range of surviving trilobites narrowed. They would persist into the Permian, but as increasingly marginal components of marine ecosystems rather than dominant ones. Fish groups showed mixed responses. Placoderms, the armoured fishes that had been diverse and often dominant predators in Devonian seas, suffered heavy extinctions and would not survive long past the Devonian Carboniferous boundary. Early sharks, with their cartilaginous skeletons and different ecological strategies, fared somewhat better. Lobe-finned fishes, the group that would eventually give rise to all terrestrial vertebrates, survived, and some lineages continued their transition toward terrestrial life. The selectivity of extinction provides clues about mechanisms. Organisms requiring high oxygen concentrations were more vulnerable than those tolerant of hypoxia. Organisms restricted to shallow carbonate platforms were more vulnerable than those able to inhabit a range of depths and substrate types. Organisms requiring stable warm temperatures were more vulnerable than those with broader thermal tolerance. The victims shared characteristics that, under the specific conditions of the Late Devonian crisis, became fatal liabilities. Geographic range also mattered. Organisms with broad geographic distributions, present in multiple ocean basins and across wide latitude ranges, were more likely to survive because populations in different regions might experience stresses at different times or intensities. Some local populations could serve as refugia, sources for later recolonization. Organisms with restricted ranges, endemic to particular regions or habitats, lacked this buffer and faced extinction if their specific habitat was eliminated. The speed of environmental change relative to generation time influenced survival. Organisms with short generation times and rapid reproduction could potentially evolve adaptive responses within the time frame of environmental change. Organisms with long generation times, such as large, slow-growing reef organisms, could not adapt quickly enough. The Late Devonian crisis, despite unfolding over millions of years by human standards, occurred too rapidly for many long-lived organisms to mount an evolutionary response. The cascading effects of extinction compounded the losses. When primary reef builders like stromatoporoids disappeared, the habitat they created disappeared with them. All the organisms specifically adapted to live in reef crevices, feed on reef organisms, or shelter within reef structures lost their habitat, and many went extinct even if they were not directly vulnerable to anoxia or cooling. The ecosystem-level collapse meant that extinction of foundation species triggered additional extinctions of dependent species. The ultimate legacy of the Late Devonian extinctions was a fundamentally reorganized marine biosphere. The Carboniferous ocean that emerged after the crisis was not simply a depleted version of the Devonian ocean, but a different kind of ecosystem with different dominant groups, different ecological architectures, and different patterns of energy flow. The victims of the crisis left empty niches that would be filled by evolutionary innovation over the subsequent millions of years, but the specific ecological structures they had created were lost forever.